Good morning, champs. In this task, we need to determine the reaction rate for the species A. The task gives us a reversible reaction. So what this means is that the reaction will take place from left to right, as well as from right to left. On one side, the species A and B are the reactants, which react with the rate constant K1 to the products P and Q. At the same time, P and Q are reactants as well, as they will react with the rate constant K2 to A and B, which in this case are products as well. The task also specifies that we have a first order reaction for all reactants. Because all given species are reactants, depending on the site of the reaction we're taking a closer look at, and the task also specifies that we have a first order reaction for all reactants, we can write down for the reaction orders for alpha A is equal to alpha B, which is equal to alpha P, which is equal to alpha Q. Because it's a first order reaction, all of these are going to be 1. Like I said before, the reaction will take place from left to right and right to left. So the reaction rate of the species A is going to be equal to the reaction rate which takes place from left to right, which we'll name RA1, plus the reaction rate which takes place from right to left, which we'll name RA2. On the first step, we will take a closer look into the reaction rate RA1, which considers the reaction from left to right. So the reaction which we need to consider here is where A and B react with a rate constant K1 to the products P and Q. Because the reaction is taking place from left to right, the left side of the reaction, where we have the species A and B, are going to be our reactants, and the species on our right side are going to be our products. So the stoichiometric coefficient of the species A for the reaction rate RA1 is going to be -1. Resulting in the reaction rate RA1 being equal to the stoichiometric coefficient of the species A for the reaction rate RA1, which we just determined is -1, times the rate constant K1 times the product of the concentration of our reactants, which is the concentration of the species A times the concentration of the species B elevated to the corresponding reaction order. So Ca elevated alpha A, which is 1, and Cb elevated alpha B, which is 1 as well. Now we are going to take a close look into the reaction which takes place from right to left, which we named R82. In this case, P and Q react with a reaction rate of K2 to A and B. So in this case, the right side of our equations are our reactants, as they are reacting to our products A and B. So in this case, the stoichiometric coefficient of the species A for the reaction RA2 is going to be equal to +1. Because in this case, A is a product. So the reaction rate Ra2 will result in the stoichiometric coefficient of the species A for the reaction rate Ra2, which is 1, times the rate constant K2 times the product of the concentration of our reactants, which in this case are Cp times Cq elevated to their corresponding reaction order, which in both cases is equal to 1. So the reaction rate of the species A will result in the sum of the reaction rate Ra1 and Ra2, as in this way we will be considering both sides of the reaction. So the result is going to be equal to -1 times the rate constant K1 times Ca elevated 1 times Cb elevated to 1 plus +1 times the rate constant K2 times Cp elevated 1 times Cq elevated to 1, which we can simplify as following. In this task, we need to determine the reaction rate of the species P for a series of reactions. In the first part, the species A reacts to the species P with a rate constant K1. In this case, P is a product. In the second part, the species P reacts to the species Q with a rate constant K2. In this case, P is a reactant. The task also specifies that we can assume a series of reactions to be elementary reactions. And for the reaction rate of the species P, we need to consider both reactions. So the reaction rate of the species P is going to be equal to the first part of the reaction where A turns into P, which we'll name Rp1, plus the reaction where P turns into Q, which we will just call Rp2. So let's firstly analyze the reaction rate Rp1. As I just said before, for the reaction rate Rp1, we're only going to take into consideration the reaction where A turns into P with a rate constant K1. So in this case, A is going to be our reactant and P is going to be our product. So the stoichiometric coefficient of the species P in this case is going to be +1 because P is a product here. So the reaction rate of the species P, Rp1, is going to be equal to the stoichiometric coefficient of the species P in this case, which is +1 times the rate constant K1 times the product of the concentration of our reactants, which in this case is only the concentration of the species A, elevated to its corresponding reaction order alpha A. So the task specifies that we can assume elementary reaction. Hence, we can assume that alpha A is going to be equal to the absolute value of the stoichiometric coefficient of the species A, which is -1, and the absolute value of it is 1. This will lead in Rp1 resulting positive 1 times K1 times Ca elevated alpha A, which is 1. Next, we will take a closer look into the reaction rate Rp2, which only takes into account the reaction where P reacts with a rate constant K2 to Q. In this case, P is going to be our reactant and Q is going to be our product. So in this case, the species P is a reactant. So the stoichiometric coefficient of this P for this reaction part is going to be equal to -1. So the reaction rate Rp2 will result in the stoichiometric coefficient of the species P, which is -1 for this reaction, times the rate constant K2 times the concentration of our reactant, which in this case is our species P, elevated to alpha P. Again, we can assume an elementary reaction here. Hence, alpha P is going to be equal to the absolute value of the stoichiometric coefficient of the species P, which is -1, and the absolute value of it is going to be 1. Hence, Rp2 will result in the following. -1 times K2 times Cp elevated alpha P, which is 1. So our reaction rate Rp will result in the sum of Rp1 and Rp2. So if we insert the terms we just determined, we can write it as following: -1 times K2 times Cp elevated 1.